Now, sometimes we get functions that are not able to be integrated, or we don't actually know what the function is. So what we need to do is use what we call approximation methods. Now, there's a number of different approximation methods to find an area of a function under a curve of a function, or if like we can apply these ones get applied lots to different applications in the real world. Two of the ones we do in this course are what's called the trapezoidal rule and the Simpson's rule. But as I said, there's more. There's some things like the mid-ordinate rule. And there's other types of functions that you can, other types of rules you can use. The one we want to look at now is what we call the trapezoidal rule. And really, what it boils down to is if we've got a curve, what we want to do is just create some trapezium. So if we look at this area here, we want to find, if we want to find the area on the curve here, if we create a trapezium here, we're going to find that we're going to get an approximation to the area. It's not going to be a great approximation because you can see there's area that's been missed out here, and there's area included that's not part of the action. Sorry, that hasn't been included, and the area that has been included that's not part of the curve. But it is, as I said, it's an approximation, and if we can't integrate the function, then well, we've got to go with that. We've got to go with an approximation method. So what we're really doing is just creating what we call a linear function. We're just drawing a straight line between two function points there. But what we're doing is creating a number of trapezium. All our trapezium we take are going to be the same distance apart, so we get the idea of what we call h, which is our common distance. So we can draw a number of strips here. If we split it up and say that's h and that's h as well, then we get two trapezium that we can do. And then we can split it up as many times as possible. Again, the more we take, the more splits we do, and the smaller the value of the h is, the better it's going to be in terms of our approximation. But again, that starts to be a little bit harder. Really, it only starts to be that easy when you get a computer. The formula we're going to use, we use h over 2 and use our first y value that we take and our last y value, and then 2 times all the y values there we're going to get. So there should be a function of x1 there. So we've left out some notation there. I'll use function of x0 if you want to. In some of the notes you'll get cy0 yn, because we're actually taking the y values, and then y1 plus y2 and so on to the second last value. And I always prefer to use the idea of using the words for these ones, because that starts a little bit ugly. H over 2, and then the first y value, the last y value, and 2 times the sum of the rest of them. We're not sure how to find h. H is often used as our limits of our function. So we say b minus a if b and a are our end values, over the number of strips we're going to use. So how many intervals are we going to use? So let's have a look at some examples here. We're looking at all of these values and using the trapezoidal rule here to approximate the area of this one. The block's 60 meters long, which means if we've got 6 there, split up 6 times, each of those is going to be 10. So that's how we get 60 divided by the 6 strips gives us 10. So that's where n comes in, over 2. We're going to use our first y value, our last y value. There's the 12 plus 13, and then 2 times the rest of those functions. And that's going to give us an area of 1010. So that's the application of the formula there with all those values. Again, using the table here, we can see that our h value goes up a half, up a half, up a half. So our h value is a half there. Our first y value is 0, our last y value is 0.27, and then 2 times the rest. So 2 times 0.3 plus 0.37 plus 0.33. And then put it into the calculator to one decimal place. Question 3 here, trapezoidal rule with 2 subintervals. So that means if there's 2 subintervals, it means there's 3 function values. So that's an interval there, and that's an interval there. So again, we're going up by 1. It's 1 to 3, so two sub-intervals. So 3 minus 1 divided by 2 is 2. Is 1. So that's where we get the h from, because it goes up by 1. And then we have our first y value plus our last y value, 2 times the rest. Well, it's only one value, so 2 times the half, and then throw it into the calculator. And again, we see 0 to 5. We've got 6 function values. This is what we call 5 sub-intervals, or 5 strips. So again, we can see it goes up by 1 each time. Usually they're nice numbers they go up by, because again, we want to make it as easy as possible. So h is 1, and then we use our first value plus our last value, and then 2 times the sum of the rest to give us our answer there, and just put that into the calculator. So try to remember the formula. Again, I don't remember in terms of symbols, I remember in terms of words. So the h on 2, the first y value plus the last y value, and then 2 times the sum of the rest of the values.